in the previous class we started discussing capacitors. We calculated the capacitance of a spherical capacitor of concentric spherical capacitor by using two methods. The first method was Q method, in which we assume a certain charge distribution, a reasonable charge distribution on the conductors that constitute the capacitor, and in the second method we called as V method. We solve Laplace's equation and find the electric field, find the total charge that is contained on the conductor, and the ratio of those will give us the capacitor value, right, capacitance of the capacitor. Here we will continue to find capacitance of some practical structures. The capacitance that we are going to consider now is something that is very familiar to you guys. This is called parallel plate capacitor. Okay. Parallel plate capacitor is something that you are familiar with whenever you talk of capacitor. Even those who do not necessarily do this course or will never do this course in their lifetime will still probably have an idea of what parallel plate capacitance would be. The formula for that is fairly simple, that you can remember it. It is epsilon A by D, where A is the area of the plate of the capacitor and D is the separation between the two plates. So, let us see where this famous formula comes from and also see whether this is actually valid or not valid, or if it is valid, how much is this valid. Okay. So, parallel plate capacitor simply consists of two parallel plates, right. So, it consists of two parallel plates of same area and make. Both of them of the plates are composed of conductors with conductivity sigma, which can be thought of as to be infinity, and then you apply a potential, right, by a battery by connecting the two plates. Okay. Now, because of this potential that is applied, we know that there will be charges induced on the top and bottom plates. Okay. The charges are induced from the top and bottom plates, and there will be an electric field from the top plate to the bottom plate, right. So, if we start looking for expression for capacitor, capacitance of this structure, let us first consider the Q method. In the Q method, we will have to assume a certain charge distribution. So, a reasonable charge distribution that you can assume is that of a surface charge density rho s. So, we assume a surface charge density of rho s coulombs per meter square on the upper as well as on the lower plates of the capacitor. Okay. Now, from boundary condition that you have seen, we know that there will only be normal component of the electric field from the top surface or the top plate, correct. So, if you recall what the boundary condition was, you have a conductor and you have free space or a dielectric. Of course, we will assume that there is a dielectric epsilon sitting in between these two. So, conductor and a dielectric, we have already seen from the boundary condition that there will only be the normal D component, okay, and this normal D component will actually be equal to the surface charge density on the surface of the conductor, right. So, we have seen this from the boundary condition. Now, we also know that Dn will be related to the electric field, normal electric field. Dn is equal to epsilon En. So, this will be equal to rho s, which gives me a uniform electric field which is all normal to the plate, and this is given by rho s by epsilon volt per meter. Okay. So far so good, fine. Now, what is the potential difference between the top and the bottom plate? So, potential difference between say the top and the bottom plate, okay, is obtained by the line integral, and this line integral is that of the electric field rho s by epsilon times some dx. So, okay, if you call this as x is equal to 0 and this as some x is equal to d, then the line integral which you are taking will be dx, and an appropriate path is what you are considering. So, say from d to 0, and the potential difference will turn out to be rho s by epsilon into d. Okay. I am not distinguishing between whether this is 0 to d or d to 0, because simply I am interested in the potential difference, not in the exact potential of the top and the bottom plate. Okay. So, for the configuration that we have written in this way, the potential difference will be from the top to bottom plate will be equal to rho s d by epsilon. So, if you connected the positive supply to the upper potential, then the upper plate will be at a potential of rho s d by epsilon with respect to the bottom plate. Okay. So, this is the potential difference. Now, you already know what is the charge density, right. The ratio of these to the capacitors can now be obtained by Q by delta V, where Q is the charge that is contained. So, how much charge is actually contained? If the plate has an area of A, right, the total charge contained will be equal to rho s into A, correct. So, if there is a uniform surface charge density here on the upper plate as well as on the lower plate, the total charge contained will be equal to the surface charge density multiplied by the area. So, this will be equal to rho s into A. Now, divide this one by the potential difference that exists between the plates, which is rho s d by epsilon. Rho s clearly cancels on both numerator and denominator, and you will be left with epsilon A by d. This is the formula for the capacitance that we were looking for. Unfortunately, this formula is wrong. Now, we actually do not really say that it is wrong, it is a very good approximation. This is very good approximation and something that is very handy to use, okay, to the actual capacitance of a parallel plate capacitor. To see why this is not exact, but this is approximate, you have to see what is happening at the edges of the plate. Okay. For reference, I am showing you what is happening at the edges of one of the top plate and the other edge of the bottom plate, but you have to remember that these edges are, there are 4 edges, right. So, at all edges this is precisely what is happening. So, the field is uniform in the center, no doubt. The field lines start from the top plate and they would drop down to the bottom plate. Okay. This is perfectly all right. However, the charges that are there at the edge, they have accumulated, right. So, these charges not only give you the electric field in the direction downwards, but there would also be an electric field in the tangential or in the horizontal directions, right. So, the electric field lines would also start looking to have some non-zero tangential component, and they would sort of go from the upper plate to the lower plate by following a curved path, in addition to the uniform downwards path that we have shown earlier, which is valid in the center of the capacitor. Now, at the edges of the capacitor you have these curved paths. These curved paths or these curved electric fields are called as fringing fields, and any capacitance which or any capacitor which has this finite area or edges, wherever there are edges, there would always be these fringing fields. Okay. It is important that there is fringing fields are there only in the edges, So, if there are capacitors which have edges, there would be these fringing fields, and fringing fields also contribute to the capacitance, right. So, the one capacitance that you have seen is the capacitance in which you have placed a uniform dielectric down here, but there would also be a capacitor that would exist between these top and bottom places because of the fringing field. So, the capacitor is actually because of the uniform electric field, okay, plus the fringing fields that exist because of the edges, charges associated with the edges. And in calculating the capacitance of a parallel plate capacitor, we have completely neglected this fringing field. We are able to neglect this fringing field only when the area of the plate is very large compared to the plate separation. So, only when A is much higher compared to the plate separation D, then we can say that the capacitance is epsilon A by D, and that actually forms a very good approximation. Otherwise, this is not really true because fringing fields have been neglected. It turns out that to include fringing fields in a closed form expression is very difficult. Okay. Therefore, what we normally do is we actually use a numerical method such as method of moments, a popular method to find the fringing fields. We calculate the actual charge distribution that happens by taking into account the edges, and from there calculate the charge enclosed, calculate the potential difference, and calculate the capacitance. Okay. And it can be shown that those calculations that we do actually much more, correspond much more closely to the experimental values. This epsilon A by D is valid as long as A is much larger than D. Say A is about 10 times the separation, then this expression is very good. Okay, this was for the Q method, right. How do we actually use another method, which was the V method, to calculate the capacitance? To obtain V method, we need to solve Laplace's equation, right. So, again going back to the assumption of neglecting fringing fields and assuming everything to be uniform, the Laplace's equation solution in we can look at the solution in Cartesian coordinate system. The plates are assumed to be in the Cartesian coordinate system, described by the Cartesian coordinate system. and since the field lines are all uniform and going in only a particular direction, I can take this as with only one variable. Okay. So, I have d square v by dx square is equal to 0, and that is only one variable that is necessary for me. How do I solve this? Well, integrate this one twice. So, v of x will be equal to, first integral will give you some constant k1. So, that will be dv by dx is equal to k1. The second time you integrate, you will get k1x plus k2. Again you have v at the top, which is valid at x is equal to 0. At the top plate is the applied potential difference or the assumed potential of V0. So, V0 will be equal to K2, and V at the bottom, okay, since K2 is equal to V0, this becomes K1x plus V0, okay, and at the bottom surface x is equal to d. So, the potential is 0 there, and this would be d K1 plus V0, which implies that K1 is equal to minus V0 by d. Is that correct? So, d K1 plus V0 is equal to 0. So, d K1 into d is equal to minus V0, therefore, K1 is equal to minus V0 by d. So, if you can put these two into the solution, so you will get V of x as V0 minus x V0 by d. Okay. So, at x equal to 0, this has a potential of V0, at x equal to d, this has a potential of 0. So, this is the potential function between the two parallel plates, and you can see that the potential is linear. Okay. You will see linear potentials whenever there is uniform electric field. Whenever electric field is non-uniform, only then you will see some different potential that is not a linear potential. Okay. In this case, the electric field assumed to be uniform, therefore, potential is linear and it is given by V0 minus x V0 by d. Okay. What is the electric field? Electric field you did not have to do anything, right, it is actually uniform. And what is the electric field? Electric field is minus del V of x, that is gradient of x. Gradient will give you minus del by del x of V of x along x direction, and if you differentiate this quantity with respect to x, you will get minus V0 by d. There is already another minus because of this minus condition. So, it actually becomes V0 by d into x hat. So, this is a uniform electric field directed downwards along the x axis, and it is given by V0 by d. Okay. Next, what we should do in order to compute the potential, I need to know the charge distribution, right. So, to obtain the charge distribution, I can consider the plate, okay, of the area A. I know what is the electric field that is coming down here. So, I also know what is d field now. D field will also be along x direction, and it would be given by epsilon V0 by d, because d is equal to epsilon E. So, this will be d equals epsilon V0 by d along x direction itself. The total charge enclosed will be given by the magnitude of d into A, because d field is everywhere perpendicular to the surface area of the top or the bottom plates. So, this will be equal to epsilon V0 A by d. This is the total charge that is enclosed. Now, capacitance is given by charge divided by the potential. The potential applied is V0. So, clearly this will be equal to epsilon 0 V0 A by d divided by V0. V0 cancels on both sides and you are left with epsilon A by d. Okay. So, this is the capacitance that we were looking for earlier in the Q method, and we actually obtained the same result using V method. Now, it is interesting that when you look at the ratings of a capacitor, capacitors are given a certain rating, okay, in terms of a voltage. There is a maximum voltage that you can apply across a capacitor. If you apply more than the voltage that is rated, then there will be arcing between the capacitor, and the capacitor simply gets damaged. Why is the capacitor getting damaged? What happens is that for every dielectric that you consider, there is a certain breakdown electric field. Okay. A breakdown electric field is one. If you apply more than this electric field, which is more than the breakdown electric field, what happens is that the electric field becomes so strong that it actually rips apart the molecules of the dielectric, okay, in the sense that it ionizes the dielectric, and the dielectric will not be a dielectric anymore, okay, it becomes into a different kind of a matter. So, there is always a certain maximum electric field that you will have to apply to any given electric, any given dielectric, and this maximum electric field is called as the dielectric breakdown, okay, because beyond this the dielectric simply breaks down. So, there is a dielectric breakdown strength, and since electric field is related to the voltage, you can either quote the breakdown strength in terms of the electric field E or in terms of the maximum voltage that you can apply. So, what has that got to do with this parallel plate capacitor? Well, there is a certain maximum voltage that you can apply. So, let us call this as the maximum voltage. The maximum voltage will be reached, and assuming that you want to fabricate a capacitor with a small value of D. Why do I want to have a small value of D? So that I can fabricate larger values of capacitance. See, capacitance is inversely proportional to D for a parallel plate capacitor. So, as D becomes smaller, the capacitance increases. So, I can make it smaller, but I can't keep making it smaller, because as D becomes smaller, V0 by D, which is the electric field, that becomes larger. So, if D is at its minimum value, then the electric field associated with that, which will be the maximum, is given by whatever the applied field. Let us say the applied field is also at its maximum, and this is given by V max by D min, and this quantity has to be less than the breakdown electric field. Okay. This actually puts down a limit on how much D min you can use. The D min should be equal to V max by E break, okay, indicating that D, the separation should always be greater than this minimum value. Okay. For example, consider the breakdown strength of a given dielectric as about 30,000 volt per centimeter, okay, and let us say the capacitor is rated to work at 300 volts. Okay. So, the capacitor is rated to work at 300 volts, and it actually has a breakdown electric strength, whatever the material that fills has a breakdown electric strength of 30,000 volt per centimeter. Then what should be the minimum value of the separation? The minimum separation should be the maximum voltage that the capacitor can withstand, which is 300 volt, divided by the breakdown electric field strength of that dielectric, which is 30,000 volt per centimeter, giving you 10 to the power minus 2 centimeter. So, your separation D must be greater than 10 to the power minus 2 centimeter, so as to avoid breaking down the dielectric and damaging your capacitor. Okay. Let us look at third and one of the most widely used transmission lines or a transmission cable called coaxial transmission line or a coaxial cable, okay, or a coaxial cable. This is very important because for up to say few hundreds of megahertz one can actually use coaxial cables. Okay, there are coaxial cables which can be used up to a few hundreds of megahertz, and these are ubiquitous. You can see them in every lab, whether you are connecting a signal generator to your circuit board, you are connecting two signal generators, you are connecting an oscilloscope to your circuit board, you would normally use a coaxial cable. Okay, at least at one end it would be a coaxial cable. Okay. So, how do we calculate the capacitance of a coaxial cable? First, let us look at what is the structure of a coaxial cable. A coaxial cable is composed of two cylinders, one having a radius A and the other having a radius B. Okay. So, it is composed of two cylinders, one having a radius A and the other having a radius B, and the material in between is filled with a dielectric of permittivity epsilon. Okay. So, this is the coaxial cable, as you can see. Okay. The cable is uniform along the length that we are going to consider, and our objective would be to calculate the electric field. When I hold the inner potential at some value V0 and take the outer potential as the reference. So, outer is 0 potential and the inner one is at certain applied potential. Okay. If you recall our discussion on electric field of a line charge, you would see that we have actually already solved this problem, but we will not do that one. Okay. We will derive the capacitance fresh by calculating it using the Q method or the V method. Okay. The reason why I wanted to remind you of that we have already solved this problem is because when you considered a uniform line charge, you considered a uniform line charge of some line charge density rho L, we found that the field at any point because of this line charge would be going as 1 by r, right. It would be proportional to 1 by r, and when you calculated the potential, you found that you could not choose infinity as the point of reference, right. For a point charge we could choose the infinity as point of reference and calculate the absolute potential. For this line charge of certain line charge density, you could not use infinity as the point of reference. So, if you remember the exact calculations that we did, we actually took the ratios of this some R1 to R2, we said okay at 16.5 centimeters I have a potential of 0 potential, and then at 10 centimeters I have a potential of 5 volts, and then gradually I looked at all the equipotential surfaces. You know, if you remember that, you would remember that that was essentially a coaxial cable that we discussed, okay. And the point I am trying to remind you is that I have to take one of those potential points from a certain distance from the inner charged cylinder as the point of 0 potential and calculate all the potentials with respect to that point, not the infinity point as the point of reference, okay. With that remembering thing in your mind, let us use the Q method to calculate the capacitance, okay. So, we do not completely forget the fields of a line charge. We will assume that the inner cylinder is now induced by a line charge rho L coulomb per meter, okay. A similar minus rho L coulomb per meter would appear on the outer cylinder as well. So, with this rho L coulomb per meter, what would be the electric field? I am not going to derive this. The electric field will be rho L by 2 pi epsilon r. Hopefully, you know how this electric field is obtained. This is the radial electric field that we just described. What would be the potential V? The potential V between the 2 points is also given by let us say since I want the potential difference between the 2 points, delta V is given by integrating this ER, okay, from outer surface to the inner surface with a minus, sorry, no minus, minus sign. So, what you get here is rho L by 2 pi epsilon log of B by A, okay. This is also we saw in the last in a few classes ago. So, I seem to have everything. Now, consider a length L of the cylinder, okay. In this length L of the cylinder, what is the total charge that is enclosed by the cylinder? This would be rho L into L, right. I made a small mistake. The limit of the integral is from B to A. I wanted to put the B negative sign in front of the integral, but I by mistake put the negative sign in the limit itself. So, this is integral B to A, and you can calculate this and you will see that this would be rho L by 2 pi epsilon log of B by A. Now, coming back to this length L of cylinder, how much charge is contained in the length L of cylinder? It would be rho L into L. This is a line charge density rho L times L will be the total charge that is contained. So, the capacitance will be equal to rho L into L of length L. So, capacitance of length L will be equal to rho L into L divided by rho L by 2 pi epsilon log of B by A. So, 2 pi epsilon goes to the numerator, rho L cancels with both numerator and the denominator, rho L cancels there, and you get 2 pi epsilon L by log of B by A, okay. However, in such structures which are mainly used for transmission lines, you are not interested in the capacitance of a given length, you are interested in capacitance per unit length, okay. Because these capacitance per unit length, inductance per unit length, resistance per unit length and conductance per unit length are the parameters that we use to describe a transmission line. So, capacitance per unit length is capacitance divided by L, that is capacitance of length L divided by L, and this is given by 2 pi epsilon by log of B by A farads, okay. A fairly simple formula again to remember. Of course, here again the formula is not completely correct, because we assume that all of the charge distribution was essentially a line charge distribution of 0 extent, right, and it was all sitting nicely in the center of the cylinder, and that the cylinder was going all the way from 0 to infinity or from minus infinity to infinity, and that is how we say the capacitance per unit length is constant and it is independent of the length of the coaxial cable, which is again strictly speaking not true, because you do have to terminate the coaxial cable at some end. However, as long as that length L is large and you are not looking at the edges of the terminating ends, then this capacitance per unit length expression is quite accurate, okay. If not, well, you will always have to use a numerical method to solve this problem, okay. So, we will not look at the V method for this, you will get the same condition and it will turn out to be solving Laplace's equation in cylindrical coordinates. I will leave that as an exercise to you guys. Okay. Now, we will consider a situation that is slightly more difficult, okay, than what we have been discussing, but at the same time that is very, very important practically. Okay. This is that of a two parallel wires. Okay.